Alright, welcome to figuring out oxidation numbers. These are the main thing you are going to need in Unit 9. They're not the hardest thing, but pretty much everything runs off of these, so make sure you're paying attention. Alright, to keep track of when electrons are transferred and where they're transferred to or from, scientists basically developed and use oxidation numbers. As a reminder, oxidation is when we lose electrons, reduction is when we gain electrons. While we know that, and it's pretty doable to actually determine when you've only got, one side of a reaction and you see electrons somewhere, given a typical equation, it gets hard. So we use oxidation numbers. Now these numbers are typically going to be positive or negative whole numbers, sometimes even zero. They refer to when electrons lose or gain. Meaning, if we have a positive oxidation number, that's an O(N) for oxidation number, that means that we've lost some electrons. So if we have a positive 2, that means we're kind of assuming this is going to lose 2. Positive 3, lose 3. It's not the same as their charge always, but it's getting us the idea that it's basically going to lose 2. A negative oxidation number is when they've gained electrons. So negative 2 means it's going to basically gain 2 electrons. At least it's going to be more in control of 2 electrons. Finally, though, a 0 oxidation number means nothing really changed with this. That means nothing's going to happen. It's not going to gain. It's not going to lose. It's just going to stay how it is. So again, oxidation numbers deal with electrons and where they've been transferred. If it's positive, they've lost them. If it's negative, they're going to gain them. And if it's 0, nothing really happens to them in this reaction. If all of the oxidation numbers are 0, we do not have a redox reaction because no oxidation has occurred and no reduction has occurred. No electrons have been transferred. Assigning these require using the following list. You must go down this list in order, meaning go to number 1 and then go to number 2. Only go to number 2 after number 1. Make sure you go in order. You will get different answers if you do not, and they will be wrong if you do not. Number 1. All elements in their natural state are 0. This means that elements in their natural state, if they're just chilling by themselves, are not really going to be in more control of electrons because they're just by themselves. There is no one to take or give electrons to. When you're walking by yourself and you're talking to yourself, people are going to think you're kind of weird. Or if you're sitting in your classroom at 4:40 in the afternoon and Mr. Martin walks in for the stock room, he's going to think you're weird. He literally just did that. Because there's no one to really talk to. There's no one there. You're not talking to them. You're not listening to them. Now, I'll be honest, there's psychology that says talking to yourself is great. Keep doing what you're doing. But in oxidation numbers, elements by themselves, typically in their natural state, have a 0 oxidation number. For example, that means that if we got sodium chilling off by itself, just in a random reaction, it's going to have a 0 oxidation number because it's sodium chilling off by itself. Okay, also, the hydrogen in H2 is by itself. Wait, Mr. Booth, this dude's there's H2, there's 2 of them. Yeah, this is like you walking around with your clone. It's still weird, let alone the fact that you got a clone. It's just hydrogen. It's just by itself, and hydrogen's natural state is in pairs. You're always going to see it by itself. Like junior high girls, you always see them in pairs. It's weird, but that's just what you do. Lastly, for lack of a better term, we got this weird freak of nature, sulfur in S8. It decides to come in 8 pairs. So apparently, 1 clone wasn't enough. It cloned itself 7 times, and it walks around all holding hands and skipping. It's freaky. No one talks to them, so we have a natural oxidation number of 0. Elements in their natural state, or commonly by themselves, will have an oxidation number of 0. All right. Rule number 2. All monoatomic ions are their charge. Mono means 1. Atom means atom. Ions mean they have a charge. So if I have a charge of 2+, that's my oxidation number, positive 2. If I have a charge of 3- and I'm by myself, I've got a charge of negative 3. For example, Calcium in calcium 2 plus has an oxidation number of positive 2. We deal oxidation numbers with the atoms and the elements, not with the numbers. That means that we are telling me the oxidation number of calcium. You are not telling me the oxidation number of calcium 2 plus. If anything, you are telling me the oxidation number of calcium when it looks like calcium 2 plus. We are dealing with the elements, not their funky little form that we're looking at. That means that calcium is at a positive 2. Also, we have another example. Sulfur and sulfur 2 minus, which is commonly called sulfide, is negative 2. It has an oxidation number of negative 2 because it has a charge of 2 minus. Please make sure you know those are different. Charges have the numbers first because they tell me how many extra positives or negatives I have. Oxidation numbers are weird. We have a positive and negative in front for no real obvious reason except just to be different. Okay? Lastly, aluminum in aluminum 3 plus is a positive 3. I'm sorry, not really sure why I put the 3 there instead of a positive, but it should be. So again, to kind of recap and review so far, aluminum versus aluminum 3 plus. Our first rule is that all elements in their natural state or when they're by themselves are 0. This is aluminum by itself and has an oxidation number of 0. This is an aluminum with a charge. Anytime you have one ion chilling by itself with a charge, it's called a monoatomic ion because you have one atom. That atom then, its oxidation number is 3. Its charge, which in this case means positive 3. By itself, 0. With a charge, the charge. Yay. Next one. All right. So if it's not by itself, or if it's at least not by itself with a charge, then typically it's probably in a group. You know, if it's not by itself, it's got some friends. To start with, the very first the only real elements that actually always have the same oxidation number are group 1A metals and group 2A metals. If you don't know what group 1A and 2A are, look at the periodic table. At the very first 2 columns at the top, it says 1A and 2A. There you go. You now know the group 1A and 2A metals, except hydrogen. Hydrogen's not a metal. You probably know that. And if you don't, you should. Hydrogen is not a metal. That means that these are lithium, sodium, potassium, rubidium, cesium, and francium, or beryllium, magnesium, calcium, strontium, barium, radium. These are the 1A. These are the 2A. That means that every single one of these in a compound is going to have an oxidation number of positive 1, and every one of these will have a positive 2. I don't know how I can remember that, Mr. Booth. Well, it has a 1 in the 1A, so it's got a 1 oxidation. It's got a 2, so it's 2. There you go. You know how to learn it. For example, let's get some practice. Sodium in NaCl is plus 1. Sodium is a 1A metal. It's got a plus 1. Also, magnesium in MgF2, that 2 is supposed to be small. Sorry about that. It's plus 2 because magnesium. Elements by themselves are 0. If they're by themselves with a charge, they're their charge. And then the first 2 columns, the first column is a plus 1 and the second column is a plus 2. Or group 1A metals are plus 1, group 2A metals are plus 2. All right. Step 4. Oxygen is usually negative 2. But for some reason, it's negative 1 when it has a peroxide. Okay, here you go. Oxygen. Oxygen as itself, by itself. Peroxide. A lot of times when you see O2, it's going to be peroxide. For example, in the compound hydrogen peroxide, it's going to be a peroxide. Most of the time, it's just going to be negative 2. Every now and then, it's going to be actually 2, like, as a peroxide, okay? Gets a bit weird. I'll show you in a bit a better way to find that. But the easiest way is to know when you're dealing with a peroxide. How you know is you memorize your common ion sheet. Get working on that. Practice. Oxygen in water is negative 2 because water is not dealing with a peroxide. It's dealing with the oxide. We call it dihydrogen monoxide, not monoperoxide. That'd be weird. So oxygen in water is negative 2. However, oxygen and hydrogen peroxide. Oh wait, sorry. I had something in my throat. Sorry. Peroxide. Yeah, that's a negative 1. We call it peroxide because we're using peroxide. We also don't call that hydrogen diperoxide or di anything because we're dealing with ions in this case. This compound is hydrogen and peroxide. So we call it hydrogen peroxide. So that's why it's 2 minus, etc. Oxygen is normally -2. Cool. Step 5. Kind of as a reminder, elements by themselves are 0. Ions by themselves with a charge are their charge. Okay, group 1A metals are +1. Group 2A metals are +2. Oxygen is -2. Hydrogen is normally +1. That is when it's bonded with nonmetals. Pretty much every stinking compound I'm going to give you is bonded with nonmetals. But occasionally, it might be bonded with a metal. For example, in that case, in that case, -1. Okay, hydrogen, by the way, has a very decently low electronegativity. That means basically how strongly are its electrons held to itself. With nonmetals, they are higher, meaning they can take electrons from hydrogen, so it will form a positive charge and they will lose it. Whenever hydrogen forms with metals, the metals are actually lower, which means hydrogen takes from them, which means it has a negative oxidation number. So, as usual, for example, hydrogen in NH3 is a +1. Those are nonmetals. Nitrogen is a nonmetal. That means a +3. However, in sodium hydride, sodium is a metal. That means nitrogen is probably going to be a -1. Elements are 0. Monatomic ions are their charge. 1A is +1, 2A is +2. Oxygen is -2 normally. Sometimes in peroxide it's -1. Hydrogen is +1 with nonmetals and -1 with metals. Alright, next one. Halogens are usually -1. Halogens are the second to last column in the periodic table. Okay, they are typically -1. They have stinking high electronegativities. They will almost always take electrons from other atoms, especially fluorine. That will always be a -1. The rest are usually -1. For example, if this being -1 would make oxygen not be -2, oxygen gets priority, and this actually gets to whatever it is. Keep in mind we follow rules between 4 has higher priority than 5, which has higher priority than 6. We'll eventually get to the point where that actually matters, but that's hopefully you notice some of these started saying usually instead of always. This is commonly -1. Fluorine's actually always -1. But again, you don't contradict previous rules. Anyways though, for example, fluorine in sodium fluoride is -1. It's always -1. It's fluorine. But especially in sodium fluoride, it's -1. Also, bromine in calcium bromide is -1. Okay, that's -1. It's a halogen. Yay. That leads us, finally, to rule number 7, our last one. Rule 7 states that the sum of oxidation numbers of all atoms in a compound have to equal the compound's charge, or 0 if the compound's neutral, because then its charge is basically 0, meaning all the atoms and their oxidation numbers have to add up to their charge. So if there are 2 atoms of something with an oxidation number of 2, then each of them are bringing 2 for a total of 4 being brought, like 4 positives or something. It's back with balancing charges from a long time ago that hopefully you kind of know what you're doing. But let me show you some examples. In water, hydrogen is going to be +1 and oxygen is -2. Let me show you why. Typically, I write the actual compounds formula like this, and I start actually writing its oxidation number charges over here, and kind of use this bottom part as like my scratch paper. So, the first rule that I come to that helps me with this is rule number, I believe, 4, where oxygen is -2. So I write a -2 up here. Rule 7 helps me figure out the rest. Okay, so does rule 5, but we'll get there. Rule 7 says the sum of all the numbers have to equal the charge. Well, the charge in this case is 0. So basically what I do is I say that, all right, if I have 1 oxygen atom, because, there's no subscript, that means that I have a total of 2 negative charges. I need to get that to 0. Okay, so I realize that I need a total of 2 positive charges because I want this to equal my charge, which is 0. All right, that means hydrogen has to bring in a total of 2 positive charges. There are 2 hydrogens. So 2 divided by 2, with this 2 being how many I need, and this 2 being my subscript, gets me 1. That means hydrogen is a positive 1. So again, oxygen's negative 2. We have 1 of them, so I have a total of 2 negatives. My charge is 0, so I need to add some number to negative 2 to get to 0, which is positive 2. My hydrogen then, both of those are bringing a total of 2 positives, so each individual one is just going to bring 1. That means it's got a positive 1 charge. All right, let me show you another example. In calcium bromide, calcium's positive 2 and bromide's negative 1. Okay, again, I start working with this. Okay, the very first rule that helps me is rule 3. It says group 1A metals are positive 1 and group 2A metals are positive 2. We got positive 2. That means I've got a total of 2 positives. My charge is 0, so I need to add a negative 2 to get this to equal to 0. I have 2 bromides. That means I've got negative 2 divided by 2. Gets me a 1. That means each of them are bringing 1 negative. Now, yes, this works coincidentally because each of these happen to have their own rule with it. Most of the time that won't occur. You're going to have compounds with like +7. It's weird. But this is still the process. It's just take what you know and use that to solve what you don't know. All right. You now get to assign oxidation numbers for each atom in the following compounds. Have fun. Spend a little bit, spend a few minutes, use those rules, then come on back. All right, here are the answers. If you didn't get them, you didn't use the rules. If you follow the rules I gave you, you will always be able to get these. The only exception may be this one right here. Okay, thing you got to remember, at least that helps me remember it, is carbonate happens to have a 2- charge. Sometimes I take these and break this into iron 2, and I look at this as carbonate 3. But then I remember that carbonate itself is 2-. That means we've got a negative 2 for a negative 6. We need to get to negative 2, so that's a positive 4. These numbers stay the same. And if I have 3 2 negatives, that means I've got a total of 6 negatives. That's being brought by carbonate. That means iron has to bring a total of 6 positives for 3 positives individually. Every other ones, you're just following the rules. Go learn the rules. Go memorize them. Look back at this video if you're able to. But here's some more examples. All right. Determine the oxidation number of chlorine in each of the following substances. All right, come back in a bit. Try them. Okay. A +5, B 0, C +7, D is +1. Again, use the rules. This may be the hard one. Hypochlorite, or actually perchlorate, sorry, has a charge of -1. Common ion sheet will help you know that. Those are oxidation numbers. Except one last part. If the oxidation number increases, that means it has been oxidized. Okay, that is actually the whole point of all this. If my number goes up, it's oxidized. If it goes down, it decreases. Meaning, if over here it's 0 and over here it's +2, oxidize. Or if over here it's -1 and here it's -3, reduced. Find the numbers on both sides, figure out what oxidizes. All right, you get to try these. Go. Find the numbers, that'll help, then figure out what's oxidized and reduced. Oh, sorry, real quick. First off, arrow. Second off, your answers are going to be one of the reactants. Well, the atoms. Have fun. All right. In our first example, hydrogen is going from 0 to +1. That's oxidized. Oxygen's going from 0 to -2. That's reduced. Oxygen's second one is going from -2 all the way over here to 0. That's oxidized. And nitrogen is going from, I believe, a positive 5 to a positive 3. That's reduced. That sums up oxidation numbers. This is the crucial part. Watch this again. Go watch it at home. Go watch it again. Get those rules down and you're fine. Thanks for watching.